In this example, I pose and solve for you a problem involving calculating the position and velocity of the center of mass of a system. This example follows up on the inelastic car collision, which we worked through in a different video. In that problem, we imagined two cars colliding inelastically. One car was 1,800 kilograms traveling due east at 15 meters per second, and the other car was 1,500 kilograms and it was traveling 75 degrees north of east at 12 meters per second. In the previous video, we were able to calculate the velocity of the cars after they stuck together and moved away from the collision, and a number of other things. In this example, we'd like to calculate the x and y coordinates of the center of mass of the two-car system, let's say 2.5 seconds before the collision. And we'd also like to calculate the x and y components of the center of mass velocity of the two-car system at the same time, 2.5 seconds before the collision. And the reason for working through this is to compare the center of mass velocity that we calculate in this before the collision to the final velocity that we calculated in the previous problem after the collision. Because there's a connection here, it's at the heart of conservation of momentum, as a matter of fact. So let's proceed to try to determine the x and y coordinates of the center of mass of the two cars before the collision. So in order to do this, we'll have to do some simple kinematics. If we can figure out the x and y components of the velocity of the two cars, we can use kinematics to figure out where they were 2.5 seconds before the collision. If the cars move at uniform velocity, then we can just use distance equals velocity times time to find the x and y coordinates 2.5 seconds before the collision. So in the diagram there, I've drawn the two masses and two velocity vectors, and we're imagining they're going to collide at the origin. So it's pretty easy to pick off the x and y components of the velocity vector for car 1, because it's moving all in the x direction and not in the y direction. And here we're mapping x to east and y to north. So if the car is moving 15 meters per second in the x direction, then 2.5 seconds before the collision, it should be 37.5 meters to the left of the collision spot. So the x-coordinate of car 1, 2.5 seconds before the collision, is minus 37.5 meters, and the y-coordinate of car 1, 2.5 seconds before the collision is 0 meters. So those are negative because we're backing them up in time. We're imagining they collide at the origin 0, 0. So 2.5 seconds before that, car 1 was to the left of there. Now we're going to do the same thing for car 2. We need the x and y component of car 2's velocity, but here we'll have to do a little trig. We know the velocity of car 2, or the speed of car 2, is 12 meters per second, and we have that angle, which is 75 degrees. So if we want the x and y components of the velocity, we need to do sine and cosine. So you might want to take a stab at it before I reveal it, but there's how you get the x and y components of car 2's velocity. To get the x component, you need to hit the speed with the cosine of the angle, and to get the y component, you need the sine of the angle. Well, you can plug in the numbers as well as I can, and I end up with the x component of car 2's velocity to be 3.11 meters per second and the y component to be 11.6 meters per second. I hope those are right. Send me a note if they're not. So we can calculate where car 2 was 2.5 seconds before the collision by backing the car up along that line. So it's 7.75 meters in the minus x direction 2.5 seconds before the collision, and minus 29 meters in the minus y direction. So here we have, in order to calculate the center of mass position and velocity, the x and y components of the velocity of the two cars and the x and y coordinates of the two cars. And it turns out that calculating center of mass velocity and center of mass position is really just a matter of using the right formula. So here are the formulae for calculating the coordinates, the x and y coordinates of the center of mass of a system that has a bunch of parts. Basically, in the numerator, you add up products of mass times position. And in the denominator, that's the total mass. So you would add up the total mass. So as said in the book, the x and y coordinates of the center of mass are the mass-weighted average position of the system. Now there's an analogy here. This is really just like calculating your GPA. Your GPA is your credit hour weighted average grade, which is why a 5-hour A is worth much more than a 1-hour A. So in order to calculate the x and y components of the center of mass of this system, we just need to do what those formulae say. You make products of mass times position in the numerator and the total mass in the denominator. So here I've substituted in the numbers. You should look at them and see if you agree, and then also test to see if you can calculate out what the answers are. So if I did this right, I find that the x coordinate of the center of mass is minus 24 meters, and the y-coordinate of the center of mass is minus 13.2 meters. So at this point, these are really just, here's the formula, you plug in the numbers. In the next slide, we're going to try to show what the x and y coordinates of the center of mass actually tell us. So if we try to plot back on our diagram that shows the masses before the collision, where does the center of mass lie? Well, you probably guessed right. It lies it lies on a line that connects the two masses, but closer to the more massive one. So the center of mass is the mass-weighted average position. For two masses, the center of mass has to lie on a line between them, and it's going to be closer to the heavier mass. That's just the way it works out. What about the x and y components of the center of mass velocity? Well, the calculation is exactly the same. And the formula to calculate the center of mass velocity is really very similar to the formula to calculate the center of mass position. The velocity of the center of mass is the mass-weighted average velocity of the system. So in the numerator, you tally products of mass times velocity, x components if you want the x component of the center of mass, and y components if you want the y component of the center of mass, and the denominator, the total mass. So if we plug these numbers in, which I hope they're correct, maybe you want to pause the video and take a look at them to see if you agree with those numbers. And then you can also try to calculate what are the x and y components of the center of mass. I get this, that the x component of the center of mass velocity is 9.6 meters per second, and the y component of the velocity of the center of mass is 5.27 meters per second. So what do those numbers mean? Well, we can draw that back on our diagram. What does a vector look like that has those components if we locate it at the center of mass? Well, shown in magenta there is what you get. You can see that it's a velocity that is the average of the two velocity vectors there, but weighted a little bit more heavily in this case toward m1 because the mass of m1 is a little bit greater than m2. But there's something telling about this diagram. You can see that the center of mass velocity seems to be pointing right at the origin, at the place where the cars are going to collide. Well, let's explore that a little bit. What I've drawn on the diagram now is the two cars, after they're stuck together, a total mass of 3,300 kilograms, traveling at their final velocity v prime that we calculated in the previous problem. I think that came out to be 11 meters per second. So it's interesting that the center of mass velocity vector is exactly the same as the final velocity vector. And the important thing about center of mass velocity is that when two or more objects interact in a way that conserves momentum, then the center of mass velocity isn't changed. There's no acceleration that affects the center of mass. So the two masses can exert profound forces on one another, and as we found in the previous example, those forces can do work. The forces that the two cars exert on one another are unable to change the velocity of the center of mass. If you want to change the velocity of the center of mass of a system, then you need an external force to do that. Internal forces, the force on 1 by 2 and the force on 2 by 1, always add to 0 because of Newton's third law. So those forces don't contribute to the net force. They always guaranteed to be 0. So the take-home message from this example is if you want to calculate center of mass position, you use the formulas and you're going to get a spot on the line that joins two masses that's closer to the heavier one. And if you have more than two masses, it's going to be like the average position of the masses. And then you use a similar formula to calculate the velocity of the center of mass, but that has a bit more meaning because in collisions, when there are no external forces, the velocity of the center of mass is unaffected by the collision. The center of mass of the system continues to move uniformly in a straight line, according to Newton's second law.